Here in Australia, we have 2 or 3 events per year for the heaviest 13.6 kilogram weight class of combat robots. The first one in 2026 is Robowars Sportsman Skirmish and is not something I intend to miss. Originally, the plan was to compete with the second version of my flywheel flipper, but it has been put on hold due to both legal and logistical issues. Instead, we're looking at a rebuild of my first featherweight called Derive, a suplexing lifter with powerful 4-wheel drive. It had performed well across 2 open and 1 sportsman event, but was definitely showing its age.
Here is Derive in its current state. Since it fought in the finals at New Zealand about, 18 months ago, I've done absolutely nothing except take the batteries out. It is precisely as it left, plus 18 months worth of tarnishing and rust. It's pretty beat up. It's loose everywhere. Bits are bent, bits are busted. It's all pretty scratched. Doesn't look very good anymore, and these are definitely not sportsman legal. So it's going to be redone. Even if I just wanted to recut the bent bits and try it again, the tensioning system on the drive is pretty crap. You've got a lever and Allen key against the drive motor to push the tensioner out. I've just learned a lot since then. I think I can do a better job.
I had actually redesigned the machine towards the end of 2024, but this inherited what I now perceive as flaws of Mark 1. We'll be practically starting from scratch here instead, aside from reusing the valuable gubbins. Each robot I've ever built has been defined by some feature that I didn't know how to do, whether this was a complicated part to machine or an entire unknown mechanism. This time, there isn't really anything unknown about the robot. Instead of trying something new, I'm striving to make a quality product. It's perhaps infeasible to produce a zero-maintenance combat robot, but I want Derive Mark II to be as close as I can get. This starts with the frame design. The front of Mark I featured sections of plate held together with 2 long bolts that immediately bent out of shape in combat. Aside from general chunkening, the new fork blocks will be keyed into neighbouring frame elements to isolate the fasteners from impacts, a dramatically stronger design. Hinged, rubber-isolated side armour was cool, but featured too many weak members. It would be far stronger and lighter to use 2 thick, flying buttress-looking supports and trust the inherent flex in plastic armour to absorb impacts. Inherited from the yet unbuilt flywheel flipper, I'll copy across its drivetrain as it's functionally an improved version of the old drive anyway. The previous belt tensioner had to be cranked down so hard to the frame it would crush the aluminium underneath. This is improved with increased surface area and a jack screw that will make belt tensioning far more repeatable and reliable. The small drive wheels had been running with printed ABS bushings on aluminium axles. This really did work well, but switching to needle roller bearings and shoulder bolts means I can reuse parts already purchased for the flywheel flipper. It will get a small efficiency bump as a result as well. Historically, the lifter was functional but slow, which I want to improve without changing the motor or gearbox. I reckon the aluminium lifter gear was being twisted into its axle as the driving sprocket was not actually supported by anything. In addition, both shaft and gear were aluminium, which led to lots of friction. To be improved by switching to a steel shaft and adding a bushing to the sprocket. The previous jaw looked cool, but was so tall it limited rearward travel and made it difficult to release opponents. It will now be made smaller. All my feathers besides the melty brain featured HDPE side armor, which works well, but in this case I didn't have the stock when it came time to manufacture. Instead, I'll use up almost an entire roll of TPU and see how it performs. After all those changes, this is what the new machine looks like. I think it's best described as chunky, with thick aluminium pieces everywhere. Despite this, it's actually 1.3 kilograms underweight, leaving some room to add air-gapped top armor for emergencies. With a plan in place, it's time to get machining. Starting to machine the robot out of these pieces of 16 by 80 6061 flabber, much like the original Derive actually. This is the first piece, one of the drive rails. You'll see how it is clamped in the mill on either end. The part is only about this big. Now, that means there's going to be pieces here and here. You could use them for something, but realistically they're a waste. But why not just cut the stock down and machine it directly out of something that's much closer to the actual size? Well, we'll have to stick it in the vise, of course, instead of clamping it on the table. And there's more setups, and it just takes a lot longer. So I'm currently playing the trade-off where there's about $40 worth of stock that'll be wasted throughout the cutting of these bars in exchange for about a day of machine time. Now, if this was a production environment where you could speed everything up, that time difference would also disappear.
the choice is obvious. But for me right now, this has to be made as soon as possible. I've got 3 weeks, and the robot currently looks like this. Not very robot-y. So I'm going to work with this, but just be aware you could definitely use stock more efficiently than what I'm having to now. Here we have the two, oh no, you can see a scratch. Look at this one. Here we have the two rails done on the CNC. Now there's still a little bit of work to do. They need holes machined into the end and on that top surface there. But I'll do that by hand while the CNC machine is running later to save on time. So this is all the CNC operations done. I reckon they look pretty good. They're to dimension. This slot would not line up with this outer slot if the operations were not aligned properly, and they look pretty good to me. Same with this big hole and that hole there. It was designed to not be particularly high tolerance on those features, but I reckon that looks fine. Holes on top are all good. They need to be tapped as well, but again, that's a manual job while the machine's running. There you go, about 2.5 to 3 hours of work to make these, and there's a lot more robot to go. You can see here 4 smaller pieces. So you can see here we got 4 smaller pieces using up pretty much the absolute width of the stock before the tabs won't function. You can see there's tabs in there, over there, hidden, and that's what's keeping these from just falling out. having 4 pieces in the bar like this is really time efficient. Instead of 4 setups, there's 1. Instead of 4 sets of tool changes, which might be 12, 3 per part, it's just 3. Excellent. I really like making parts like this. Now, each of these will have to be individually worked on their flip side, but it's a good start. Now I'm machining the second operation for these belt tensioner blocks. Now I've got 2 in here of the same length, so that when the jaw is squeezing in, it doesn't want to rock itself, because this is the one that we're trying to work on. It's lined up to this surface, it's touched off against that surface, so this point in the corner here is our XY origin, and it's all, the height is always done off of this, because I don't know if the back of this stock is wonky, and I don't really care. All I care is that this bottom surface is, 14 millimeters to the top surface when it's machined. So if there's any deviation or weirdness in the top, machine could not care less. It doesn't even check. Got the 4 blocks, drill holes in one side, and if you see there's an odd one out, I didn't line it up properly with the block. So unfortunately, despite being otherwise fine, trash, got to make a new one. Very unfortunate. Just doing some experimenting. This is the original Derive where I obviously got the M-mill sweep back and forth, and with this sort of finish, I'd say it looks a little bit better in real life than it does on camera. It's pretty good. But just quickly as a test, I ran over it with the face mill. Look how shiny that is. And I'd argue that looks a hell of a lot better. So, I just took like 0.05, 0.1 millimeter off the top to get this. I reckon everything that faces outward is going to look like this. I think it looks, this end mill finish looks great on the pockets and stuff. But yeah, I don't know. Look at that. It's got almost like a rainbow effect going on. I think it's really nice. So because of that one armor bracket that I had to throw out, I'm going to use one of those scrap bits from the side of the long piece that we were yapping about before about it being potentially waste. Well, this one's not going to waste. It's going to become a bracket. So you'll get to see that process and the difference between the two, which is great, and hopefully see why it's a bit of a pain. Doing a before and after of these bits before they all get the shiny treatment, so these faces should get nice and pretty. To save time, we can put 2 of them in the machine at once and just go done. And swapping out for the next bits should be a pretty quick operation, because I use this face mill manually. I've never actually written a program that runs this mill. It's big, a lot of inertia. I don't know, I don't trust myself just yet. Manual operations, it's really quick. Just picking up some stock material, it made a really nice noise. So I'm going to reproduce it, and hopefully the microphone picks it up. It's got this really nice ring to it. Let's see if we get it.
Anyway, that's really cool. I hope you actually get to hear that.
Got all the plates cut up. So you got a stack of them there. They're about the size of the mill bed. Not the most efficient use of the material, but I don't have a big router, so there's not much of a choice. This saw is just running a regular old wood blade with carbide tips. Now, if you're doing a ton of aluminium, you can get more specialized blades, but these work perfectly fine. There's nothing wrong with it. That's not, you wouldn't use a wood saw on aluminium, but these carbide blades, just fine. Make a bit of a mess though. It's going to be a lot of cleanup.
Cleaning up the edge of this plate here, it's really sharp. A couple ways you can go about it. You can use a deburring tool, scrape it along. I found it sort of bites and digs, get a very nice edge. I like to use a file, of course. Now, you don't want to go along like this. Oops. You're going to end up with a very uneven, rough finish. You can see the teeth on the file and the way they're angled. So if you hold it like this, the teeth are actually perpendicular. Might have to zoom in. You can see the teeth are perpendicular to where it's going to be pushing. So you get a really nice, just clean effect as you push it through. There you go, do it at a couple of different angles. By angles I mean rotating around like this. I mean, this is now really smooth. I have no problem running my hands along this all day, every day. That's just fine. So looking to countersink these plates a bunch. You can see all the countersinks, and obviously doing all this by hand, with a hand drill would be a real pain, and they're definitely not going to be all the same. So, not that this is a particularly new technique. With these drill presses, you can set the depth they go to. Let me put this down. You can set the depth so that when you pull the lever, they'll stop at a fixed height. So stick the chamfer tool in there, and you can just smash out holes really quickly. Go, all done. Now these ones are really chattery. I'm not exactly sure why. The first ones were fine, and then it got more chattery and more chattery. Maybe the tool is wearing out. But once you drop a screw in them, no issues at all. A question you might have is, you cut these out in the CNC mill, or why not just do the chamfers in the CNC mill at the same time? Which is a fair point. The problem with these plates, particularly when you just hold them down at the corners, is that they bend a lot in the middle. Like there's a bunch of deviation in the height. Like you really can't trust it. So these chamfers would all be, if it's bending up in the middle, these ones will be really deep and these ones will be too shallow. And you can't really hold it down reliably, because where would you hold it down? Well, you put screws in the holes. Well, if you put screws in the holes, then you're not putting a chamfer tool in behind it, are you? So it's a lot easier, particularly I've designed this machine around the same screw for all of these plates. So knowing that I'm going to end up doing this and just smash them out. And all of this took maybe 5 minutes, right? Really quick. For a repeatable, easy process. Drill press, really good tool to have. I know, big surprises. But of all of the machines in this shop, if you had to pick one, it'd be the drill press, I reckon. This is the setup for bending the plate in the vise. Got some new bits of extrusion so it doesn't mar up the surface too much. You can see this is the bend that went just fine. Something long that's not going to break. I want to clamp it down low to ensure that the bottom bends with it. You don't just get like an arc. You actually want it to bend at that edge. That's what these two clamps are about.
These angle holes, I waited until the plate was bent, so I marked the center line using calipers and then put a dot where they need to be drilled just by hand using the tool mark tool. Actually just spin it by hand. Now I'll take it out and drill these manually. Not the most precise things in the world, but they don't really have to be. And that will tie everything together, and then there's just some holes on the end here that will be drilled with that piece in place, and then the robot can be assembled. Got a bunch of these wheel molds. It's taken a few attempts, but now I can just pull them out with a little bit of effort. There we go. Oh, we didn't see it, but it just comes right out. Very slight taper on the mold. I think it's 1/2 degree, maybe a little bit tough. 1 degree was very easy. Just basic bamboo PLA settings. It's not extra smooth. Just using some mold release standard stuff. There you go, reusable mold. Obviously poured a little bit too much resin in this, but this flashing is cut off really, really easily. And the wheels look good. I reckon these will work well. We have all of the wheels demolded. Now you'll see we have these ones and these ones. This is an orange pigment, and this is an orange pigment of a different brand. It doesn't look particularly orange to me, if I'm being honest, which is a bit disappointing because it's also quite expensive. I assume I'm doing something wrong, but I don't think so. I'll get a photo of each one of them. Like this was like a drop, like UV resin thing. Maybe it needs UV light, I don't know. Whereas this was like a proper orange pigment that I've been using since day one, but running out of. Oh well, the wheels came out really well. Not a single one of them is problematic. I'm sure they'll all work just fine. But yeah, that's not orange. Looking at a feature on the drive belt tensioner, we've got a pulley, it's got a bearing in each end, flange bearings. It's just a drill hole, made this part way back on the first robot. Here's your tensioner block, and critically is this is the crush tube. Fairly basic concept, but a really important one. You just put this pulley in here, stuck the bolt through, and then tighten it down to stop it from moving in the robot. You probably seize up bearings because you're crushing really hard in on them. And you want to preload it as hard as you possibly can, really, without snapping the bolt. So, of course, make a little metal tube, such as this one, stick it through your pulley, and that, of course. So now we can clamp down with our heart's content on that bolt, and this pulley will still spin just fine. It's the same principle as in Obliterator's weapon stack with that spacer tube in between the tapered roller bearings that took so many attempts to get right. It's really important, and you can make much, much stronger mechanisms by using these versus just a loose bolt on bearings, or obviously clamping down on the bearings and then they won't spin anymore. While I've got a chance, just wanted to directly compare some of the old and new parts and see what we can learn about how manufacturing methods have changed. It's been a while. This is the first feather I ever made, and so it was one of the earlier projects I ever did with the mill, and now this is of course the latest one. This is one of those internal frame rails, and this is the new one, of course. The first obvious thing is that this is just the raw stock with some pockets cut into it, versus this has been face to thickness, which is really helpful for multiple setups because the stock doesn't come in round metric sizes and might have quite a bit of tolerance on it. These webs are actually quite thin, whereas these ones are the full thickness, because I didn't want to have to flip and machine the other side. I wouldn't have been able to do it accurately. So it's ever so slightly lighter, and I could have just faced this web down on one side, but then it's not really in the middle of the loads. It doesn't matter, but it's just something that you can do without thinking now, because now that everything is made accurately, plonking it around for multiple setups is really easy. Whether I'm doing it for aesthetic or actual practical purposes, just happens. It's great. Side drive rails, these are both for the right hand side, equivalent parts if you will, and apart from the fact that this one's bent pretty badly, you can see a difference in ethos if you will from designing it. This has just got some square pockets. This had some triangulations, which doesn't really matter as much. Importantly, one thing which I started doing properly, there's practically no meat around the motor. This is only like 4 or 5 millimeters thick, whereas this I gave much chunkier sections and the motor's pushed back. Definitely something that I've learned from making this machine, and this part twice actually. These cutouts which locate the armor mounting pieces,
pretty big detriment on strength, and I don't think they really need to be located like that. The bolts do a perfectly good job. Between the two, you've got chamfers everywhere on this, on both sides, because now using the actual tools with multiple tool holders like you're meant to, swapping out the tool is no longer an arduous task. When I was making these, every single time you change the tool, change the drill bit, what have you, you have to re-zero the height of the part, which was a bit of effort, and it really stacks up. So this was designed with as few tool changes as possible. You can see there are no chamfers at all. This one, the other one had chamfers because there were wires going over it. It's got just a few sizes of drill, and I interpolated with an end mill wherever possible. And same with the ends of it. Well, you can see that one's pretty beat up. Well, whereas this doesn't really matter. Change the tools as many times as you want because they're all set up in the machine. This one's more of just a design note. The old shaft, to save weight, was aluminium. I'll get a better photo, but the Hardox arms have really dug into it and eaten quite a lot of the material, actually. So the new shaft is going to be steel, which won't last forever, but it should last dramatically longer. The shaft is also just straight up bent. It's not just worn into, it's actually quite curved. I believe that happened after the first event, and I just kept running it as it is. This new shaft should perform quite a lot better. Coming off the plasma cutter, you can see there's all this really thick dross. It's really thick like this means it was cutting too slow. Fair enough, but at least with this stuff it's really easy to get off. Just take some sort of cutter things and just have a go at it. So it's easy. There you go. You can see when it snaps off, you get a really clean edge. I'll still touch it with an angle grinder to make sure I don't cut myself, but it's a lot better than trying to grind all this stuff off. Doing a bunch of painting on the parts, as I'm sure you can see. Primer in the black ones and the very pretty gold ones. Thanks to the very hot Australian sun on this nice day, this paint is drying really, really quick. It's a dry day too, it's not just the heat, it has to be dry. It's been very humid recently. So sick, this stuff will be done pretty soon, and there's more to paint. Hopefully it can be all done today. This is the current state of the robot. At this stage, things get very serial. You can't really parallelize tasks, apart from the printer printing the side armors. Putting together, or the lifter assembly, you know, at each step you might need to make a spacer, adjust a part. You know, you plod along one at a time, and eventually the robot will be mechanically complete, and then I can go ahead and wire up all the electronics and test it. There'll be about another day and a half until all the prints are done. So I've got about a day and a half until I am now the thing keeping this from being ready rather than waiting on parts to print. We have here the lifter assembly minus the big long forks. Put together, a little bit stiff, but I assume it'll wear in pretty quick as soon as it gets used. Difference to the previous one, again using these large custom aluminium washers, nice and chunky. Aside from being able to customize them, you have to stack a bunch of off-the-shelf ones. They look really good.
That's probably the main reason I'm using them. Alongside these hex head bolts, I think it looks good. And also these, if you take your regular socket head screw, if this gets smacked by a hammer or something and it dents in the hex, then you can't use a hex to get it out. So you end up using vice grips or something. With these, as long as there's 2 faces available, you can get a spanner on it. And if you want to use vice grips on these, it's really easy to grip onto these 6 sides and replace it. So that's the secondary benefit of these things. The actual strength, they're technically weaker than the grade 12 bolts. Doesn't matter. I don't think so. They're only grade 8 or something like that. Yeah, this is looking ready to go. We'll put it into the main robot. We have the machine as it currently stands. First time it's been assembled, pretty much done mechanically, as in this could fight, right? The side armor isn't absolutely necessary, but that is currently printing. At this point, one mechanical problem to solve: the head. You can hear the gears rubbing on the plastic motor controller cover because the lifter actually doesn't hit the hard stop before the gear on the arm hits the vat. So I've got to do something about that. Then it can be disassembled, wired up. That's probably a job for tomorrow. Hopefully the last arm piece will finish printing by tomorrow night. Then you can completely assemble it and test the robot and weigh the robot. Of course, that's always an important step. But I might go to bed. I think that's a good move. To fix that problem of this gear, you can see it's rubbing on this plastic cover by a good sort of millimeter or 2 of travel was remaining. Added these screws and you can stack up washers to adjust how high they sit, and they press against this nut here and here. So when the jaw is down, no more rubbing on the plastic. Now the gears themselves need a bit of a wear in, but they still float and sit on the ground. That's sitting on that in there. That's pretty good, I reckon. This is ready to be disassembled and then wired and checked, as I mentioned before. It needs to be properly disassembled because when you tune the VESC motor controllers, you need to tune them with the motors completely unloaded. So I've got to, apart from doing a little bit of work on the drivetrain, I've got to take the belt off. The lifter gear motor has to come out of its gearbox, so that's quite a bit of work. Then the whole thing is slapped together. This here is one of the side armor thingos. Hang on, the lighting isn't very good. You can see your 2 pieces of 3D print, this polycarb plate and this aluminium plate sandwiches the join so that you can't separate them, and this polycarb being harder than the TPU, that should be able to get smacked by a hammer or something without puncturing the TPU at least better. This is just aluminium. It's mostly just because I wanted a gold accent on the front, but it's, if there's a saw coming at it, it's better than just the TPU. It's not too heavy, but my goodness, this thing feels strong. I don't know, it's hard to tell, but this might be appropriate for open class type stuff if you replace this with a thin piece of titanium or something, just to stop spinners from grabbing the plastic, or maybe that's what you'd want, who knows. Point is, this has turned out pretty well. I'm waiting for the last piece to print, and then bolt the second one on. Going to get to soldering now, so I'm just going to cover the components that this robot uses internally. 2 of these 6S 1200 milliamp hour lithium batteries in series, because you don't need much power for a lifter, and at 12S it's a very efficient machine. So this should be plenty based on previous data. Not by a lot, but it should be fine. All of the motor controllers are FlipSky VESC 6.7 Mini Pro thingos. Maybe one maker-based one that runs the lifter. The 2 of them have heat sinks on them, so these will probably be Drive. This one doesn't have a heat sink, so assuming it still works, it'll probably be for the lifter. This is the receiver, just an old FS IA6B. It's new stock, but it's an older style. These are way better than a lot of the other stuff I found for noise rejection. They're a bit chunky, but who cares? They're not smart. Who cares? They connect to the FS2A, whatever the hell it is, protocol that all of my transmitters use, and they're beefy. I've never had an issue with any of these. They're good. A pretty big back for powering the receiver and the LED, because it needs to take 50 volts and drop it down to 5 volts. Now you could use the back built into one of the motor controllers, Specifically for Robowars, they don't allow you to have the LED, power LED, running off of a motor controller back, because say that motor controller dies, then the power LED will go off, but the other two motor controllers can still have power and the robot's technically still dangerous. So you need to have that on a separate back. You might as well put the receiver on it too. At other events, maybe they don't have that requirement. You can probably get rid of this, but there's so much room in this robot that this is totally fine. 16 gauge wire for everything except maybe directly off of the batteries. You don't need much current in a 12S machine, so this is fine, very light, easy to route through things. XT60 connectors for the batteries and any big 2-pole things. And then, I don't remember exactly what these are, but these things are great for the motor phases. Definitely overkill, but they were very cheap to get a whole bag of them. And that's it, that's everything in the machine. The two drive motors, Maytech 5065. The two drive motors, Maytech 5065 220 kV, I think. Though I hear those kV ratings are a bit iffy on how true they are. The lifter motor is a 200 kV Flip Sky 5045 that I don't think you can even buy anymore, but thankfully I've got a couple spares. Could sub in any similar big censored 12S motor. Big, efficient, high torque, low speed motors that put out the power, and the whole machine is relatively low reduction everywhere, which is enabled by having these big low kV motors. Now getting ready for the first power on. We've got the mode controllers connected. There's no receiver, not even in the machine, so I've got to make sure that the voltage regulator outputs a voltage that's not going to immediately destroy it. So I put it on chocks just so the motor controllers don't decide to move. So all this tests is to see is if anything blows up, and make sure that the 3 motor controllers light up to show that they're alive. Oops. Nothing to do but to plug it in. We have 3 sets of lights. Just not getting warm. Not getting warm. The link is only halfway plugged in, so I can rip it out quicker if something is going to go wrong. There we go, a perfect, obviously it's not loaded, but how's that for 5 volts, eh? Pretty good. Cool, time to wire in the receiver, then mechanically pull all the motors off so they can be calibrated. So this drive VESC just doesn't want to connect, and it just gets hot doing nothing. So even though the lights are coming on, I'm assuming there's something wrong with this. This one is fine, it calibrates, and as soon as you enter app utilities for setting up the inputs on this, the application freaks out with some serial error and then nothing. And then it won't connect anymore, you have to restart the computer. So I'm going to assume this one's also bad, which is just great. So 2 VESCs to change. Lovely. So we have everything now functional. Right drive, left drive, and the lifter motor. Have a listen to the difference in sound. Yes, they're different motors, but it's not just because of that. So listen to this one. Now listen to this one. Because this being BLDC, just a bunch of square waves pretty much, I'm pretty sure. This being FOC, it at least tries to emulate a sine wave going into the phases, so it sounds a lot less, I don't know, dotty. I'm sure you can tell the difference in the camera. Can put the robot together, finally. Well, I hope it goes together, that's the next problem. Oops. That's not what's happening. All the electronics are compressed down inside of this cover. This stuff will fit pretty fine. So now I've got to power on to make sure it doesn't pop, because all that stuff, it should be all insulated properly, but you never know. Really hope this goes well. Pretty good sign. Just putting in the final printed block. This will be screwed into the frame. Heaps of space for the receiver. We'll fill that up with foam. You can see where the link goes. Everything else is going together. We'll put batteries in it, weigh the thing, and then test it.
With the robot complete, it was time to pack for the event in Brisbane. Derive will get 6 round-robin fights to show off the upgrades against a solid field of other sportsman competitors. Until next time.
And next up we have possibly the most sought after fight in the competition.